right? Finally, after decades of trying to figure out, why does it look like our continents fit together? Well, how is it possible that our continents could move? After decades of this, the theory of plate tectonics is finally accepted, right? So in the scientific community, this is basically fact now. Pretty much all of us believe this as a fact. However, as I said, this is a relatively new discovery. When I was an undergrad, which was recently, 2010 to 2014, many of my professors were not taught plate tectonics in college. And so this is a theory that we often just think of, oh yeah, we know that, right? It's like evolution, it's like gravity, we know that. But comparatively, this is actually a really new theory. I'm guessing your grandparents were not taught this in school. All right, so now this is a theory, now we know it. We also know that there are three main types of plate boundaries, each based on the direction of plate motion. I've already been talking about a lot of these, so hopefully a lot of what I'm about to talk about will just be reiteration and review. Now, earthquakes can occur at all plate boundaries because anywhere where two plates are rubbing up against each other, grinding against each other, that creates earthquakes. They are more common at some than others, but they occur at all plate boundaries. All right, first, let's talk about convergent plate boundaries. This is where two tectonic plates converge and collide. If one of those tectonic plates is denser than the other, such as an oceanic plate colliding with a continental plate, or an old oceanic plate colliding with a young continental plate, the denser plate will dive down and be subducted, consumed back down into the earth at a subduction zone. When oceanic lithosphere subducts, it creates a trench on the ocean floor, a really, really deep trench, narrow and deep on the ocean floor. That's on the ocean floor. On the continent, we get mountains and volcanoes produced by compaction and by the melt generated from the subduction processes. That's why we get a lot of mountains and a lot of volcanoes on California, on the coast of California, because it's on a subduction zone. Okay? Now, as a reminder, we call the creation of mountains, the process of mountains being created, orogeny. So at convergent plate boundaries, you find subduction zones, trenches, mountains, volcanoes, and orogenic events. Transform plate boundaries, these are plate boundaries where rather than material being separated or coming together, it just slides back and forth right next to each other, laterally and that's next to each other. Okay. Transform faults are also called strike slip faults. So you might hear me use those terms interchangeably. And we can have two different types of faults, two different types of transform faults, either right lateral or left lateral. And you can figure out which is which by imagining yourself standing on one plate, looking across the fault at the other plate and asking yourself, relative to you, in what direction did that other plate move? If you're standing on one side of the plate, looking across to the other plate, and the other plate appears to have moved to the right, we call that a right lateral transform fault. If it appears to have moved to the left, we call that a left lateral transform fault. So the one we're looking at right here, imagine yourself on one side of the plate looking to the other side. What direction did that other plate move in? Is this a right lateral or a left lateral transform fault? Hopefully you said right lateral, right? If you imagine yourself standing on the plate closest to us and look across to the other side, the plate farther away from us has moved to the right. Now, transform plate boundaries, as I said, occur when two plates slide laterally next to each other. They often occur as segments in between divergent plate boundaries. And this is to compensate for the Earth's curvature. Because the Earth is a round globe rather than a flat map, the divergent plate boundaries have to be separated by these transform plate boundaries. All right, so you often see these along the mid-ocean ridge. Speaking of divergent plate boundaries, right? We've already talked about this. This is what Marie Tharp discovered with that rift valley. So divergent plates are associated with rift valleys where new material is being created. Where that new material is being created, where that mantle is welling up and creating new material, that forms volcanoes, right? Because mantle material, magma, is welling up and forming new rocks with volcanoes. Anytime a divergent plate boundary is young and just beginning, right, not well established yet, it often creates a triple junction, right? I think of this as, right, picture a layer of something slightly rigid, but something that can crack, maybe like wet sand or something like that. And then imagine poking something up from beneath That slightly rigid layer that can crack on the surface often won't create a straight linear crack. Instead, it'll break off in 3 branches. We call that a triple junction. And we see triple junctions anywhere where divergent plate boundaries are forming, right? Where they're popping up, new ones are forming. The most famous one we can see on Earth right now is the East African Rift Valley, where the Gulf of Aden, the Red Sea, and the Eastern Rift are 3 of the prongs on that triple junction. And this is what is creating brand new ocean floor and will eventually separate the Arabian Peninsula from the rest of Africa.